Chapter 7, Number 41. Calculate the power output of a 14 milligram fly as it walks straight up a window pane at 2.3 centimeters per second. So, can't really draw bugs very well, but here's our bug, whatever it is. And it travels up at some constant rate. There's sort of a shortcut if you remember a formula, but I kind of walk through a longer way to sort of do it. So we say the bug is traveling this way, and I'm going to say during some amount of time, and since everything's here is constant, I don't really care what the time is, so I'm going to say in 1 second how much work is done. So in 1 second, the bug travels a distance that is 2.3 centimeters per second times the 1 second, or 2.3 centimeters, sort of duh. And the work done is going to be the weight of the bug times that distance. So the work done is 14 milligrams, but I want to convert to SI, to standard MKS. So we have to say, well, there's 1 gram in every 1,000 milligrams, and there is 1 kilogram in every 1,000 grams. And then we multiply by G, and then we multiply by that distance, 2.3 centimeters, but then I need to convert that as well, so I say, well, there's 1 meter per 100 centimeters. And if we put all of that together, we get 3.1588 times 10 to the minus 6 joules. And when we deal with the fact that we have only 2 sig figs, it's 3.2 times 10 to the minus 6 joules. Then it gets relatively straightforward because the power is the work over the time it takes. So here we did 3.2 times 10 to the minus 6 joules, and we did it by design in 1 second because I knew where I was going. So this ends up being 3.2 times 10 to the minus 6 joules per second, which is just 3.2 times 10 to the minus 6 watts. You can actually get there a lot faster, and I did this deliberately not so, because the textbook does give you a formula where they just say if the force is constant and the velocity is constant, which we're sort of assuming here, then the power is just FV. So it's going to be the weight, which is 14 milligrams times all those conversion factors. So 1 gram per 1,000 milligrams and 1 kilogram per 1,000 grams times G times the speed, which was 2.3 centimeters per second, times the conversion of 1 meter per 100 centimeters. And if you grind all of that out, you end up again with 3.2 times 10 to the minus 6 watts. So obviously faster, but it's really because we're doing what we just did there, where we assume some amount of time and then we divide the time out, and we can get the average power this way.